in the case of Altenrhein is to update its the status of the sludge treatment at the plant, which today consists of digestion, dewatering, and drying. So within NextGen, we're looking at three possible solutions: the ammonium sulfate return flow from the digester, the production of renewable GAC from dried sludge and local biomass, and the production of PK fertilizer from dried sludge and local biomass. I would like to start briefly with the first solution, that is about the recirculation of ammonia from the digester. So here the plant has been commissioned in February 2020. We are working on optimizing process parameters such as temperature and pH. We also look at determination of key process indicators such as absolute ammonia yield, yield-specific caustic soda, and heat consumption. And we did that project. We will also perform granulation tests and NPK fertilizer test. This is a collaboration between FNV and AVA Altenrhein, but also contribution from EVAC and Alpha Wassertechnik, who is in charge of building that plant. So within NextGen, we also look at the production of renewable granular activated carbon. We call it GAC. All methods have been tested with two different materials. At FNV, we look at pyrolysis, activation, performances of the GAC in terms of the absorption capacity, and finally the physical and chemical characterization. So the project here is structured in three consecutive phases. In the first phase, we call it parameter screening. We looked at how different parameters during pyrolysis and activation impact on the quality of the GAC. So here we performed laboratory scale experiment using DSC and TGA, but we also did some pilot trials to generate enough material to perform all the physical and chemical characterization that we wanted. After defining the most promising GAC, we produced them at a pilot for going into pilot experiment. So we produced two different types of GAC from sewage sludge and cherry pit. Here is a slide about the production, how production difference depending on the feedstock that we have been using. On the top, you can see the process step for dry sewage sludge up to sewage sludge based GAC. Basically consists of simply pyrolyzing activation and final sieving. While for the cherry pit, it was needed to mill them first and sieve the finest fraction. Pyrolysis was then performed at DBI Virtucon in Freiburg. And after that, after receiving the material, we had to sieve them one more time and to perform conditioning to minimize the loss of material due to floating. So here is an example of the chemical characterization that we do on the GAC. We'll look at the feedstock material first and then how it changed after activation and pyrolysis, or pyrolysis and activation. So these are results from TGA analysis of thermochemical analysis of pilot materials activated at 900 degrees with water. So on the left side, you can see dry sewage sludge, how it looks like before, and cherry pit, how it looks like before activation and pyrolysis. So they both contain a significant fraction of inert, but is much greater in the case of sewage sludge. And this difference actually becomes even more evident after activation and pyrolysis, where sewage sludge here on the three bars on the left, with different concentration of water during activation, it's mainly consisting of inert material and a very tiny amount of carbon. Vice versa, in the case for cherry pit, the fraction of inerts actually decrease after activation and pyrolysis, and this great difference in the chemical composition actually results in strong differences in terms of the production. So, for example, the yield of the production, but also performances of this GAC. So they will have different density, different absorption capacity, different active surface, and different absorption capacity. These two materials is, so at the end we decide to pick two very different materials to go into pilot experiment. So now I would like to talk to you about our pilot experiment. Here we look at, we bring these three different materials, so the sewage sludge based GAC and the cherry pit based GAC and the reference material. We fill 3 columns, pilot columns at Altenrhein, and here we look at the capacity to remove organic micropollutants over a period of 12 months. We also looked at investigation. We also looked at biofilm development over time. We want to see how GAC transform into BAC over this long time period. We operate the system for ozonation and GAC absorption at 80% micropollutants removal in 3 consecutive phases, where the first phase will be operation with standard parameters, so 20 minutes empty bag contact time and 2 milligram ozone per liter. In the future, we will adjust empty bed contact time. And finally, in a third phase, we will adjust ozonation dosage. Okay, that was it for the GAC. So now I would like to talk to you about the third NextGen solution. This is about a pilot plant for phosphorus and potassium fertilizer production. This is an example of a picture from our pilot trials. This is the pilot we've been using, consists of a feeder, a gasifier, we have a steam unit at the end of the plant, and it's all a system for filtering the off gas and an afterburner. On the picture on the right, you can see the picture of the pyrolysis unit. So within this project, we're looking at burnout. So the objective are to improve further improvement by adapting the fluidization medium at the bottom. We are aiming at total organic carbon concentration below 0.2%, and one other objective is to remove polyaromatic carbons until they are no longer detectable. We are also looking at phosphorus availability, and we are working with residence time that will need to be increased to allow replacement reaction between K and calcium. Finally, about the operating condition, we aim to replace bad material, so we will improve on bad material replacement by a more efficient screening and using a smaller bed. So finally, for what regards the pilot plant, we further improvement are planned. We will decrease the diameter in certain areas. We will add a section for burnout to improve burnout. And finally, we are working on improved screening system for bad material. So this now I would like to conclude with what are the lessons that we learned working on NextGen so far. So for now, I will focus on just our GAC solution, because this is the most advanced part of the project. We learn from production, what we learned from production of renewable GAC and from the startup of our long-term pilot experiment. So we learned that multiple criteria govern successful use of the technology. So there's a need to compromise between, for example, very good absorption and very good robustness of the filter. So a very strong material that can last long in your filter bed. So here we are looking at hardness and density. And in terms of the performance, we're looking at high adsorption and the granular activating carbon yield during production. We also learned that scale up is not precise as expected, but still small scale experience gives a good indication for the larger scale. We are still developing the part with regards to renewable GAC. So operators need to be ready to accept the remaining risk, especially for what regards the long-term performance of the GAC. With this, I would like to thank you for your attention, and we will be available to take your questions. Thank you very much.